All right, so welcome back, everyone. We are going to continue with another fantastic talk. Next up, we have Corina Grigore, who is a senior research scientist at the self-driving car company Motional, and she works on the prediction and behavior modeling team. She obtained her PhD in robotics at the Social Robotics Lab in the Computer Science Department at Yale University. And at Motional, she develops models of how agents behave on the road, with a focus on applying machine learning techniques to predict the trajectories and intentions of such agents. Today, she's going to be presenting her work on motion forecasting in the autonomous driving domain. And with that, Karina, you can take it away.
Awesome. Thanks so much. Thanks for the introduction. That was great. And hello, everyone. And thanks for being here today and for taking the time. Yeah, I'm going to go straight into it because that intro was perfect. So first, just a little bit about Motional. So the company started out as Nutonomy, a startup that focused on developing self-driving technology. And it was then acquired by Aptiv, an automotive technology expert. And ultimately, Aptiv joined forces with Hyundai to form a new partnership, and that resulted in Motional. And at Motional, we focus on building autonomous driving technologies for robotaxis, and we've maintained a long-standing commercial robotaxi service. And we have some awesome machine learning teams that have contributed to the autonomous driving and research communities through some pioneering data sets. So we've released MuScenes, which is a multimodal data set for autonomous driving, and the first to carry the full autonomous vehicle sensor suite. And it's now widely used in the research community for both perception and prediction problems. And we also contributed and have been and continue to contribute state-of-the-art publications like point pillars and point painting, these two approaches centered on perception, and they contributed novel point cloud encoders and camera lidar fusion methods for object detection, and CoverNet, of course, which is an approach for motion prediction that I'll be going into depth today. And you can see, of course, the full list of publications on our website, so please check those out. So what does motion prediction entail for autonomous driving specifically? Well, we want to understand how road actors such as vehicles, bicyclists, and pedestrians behave and interact with each other. And we want to model the possible future states of the world. And the goal is then to use this understanding in order to make useful predictions of these actors' future behavior, make use of such predictions for planning to either have access to this information or even incorporate it in a more tightly integrated way, like with machine learned planners. We might want to create high fidelity simulations in which we use smart actors. And for that, we need to be able to make these intelligent predictions of how they will behave on the road. And we can also use it more broadly for evaluating just behaviors more generally, and this has applicability on really every level of the stack. Why is doing this so difficult, though? I think you all have a pretty good idea of the challenges within motion forecasting, but to name a few important ones here, specifically for the self-driving context, we know that it's important for us to interpret scene context to start with and to understand what's going on. So for example, a pedestrian who's stopping on the sidewalk might want to cross the road, or maybe they're just waiting there. So we need to understand whether they're going to cross the road or not, so that the AV knows if it should stop or not. We know this problem is inherently multimodal, as illustrated in this image to the right on the slide. And you can see the different options that the white vehicle has at this intersection, going straight, right, left, where you can see that a unimodal approach would not do well due to averaging of behaviors here. We know that also agents interact with each other on the road, and this interaction causes their behavior to evolve over time in a very tightly coupled way, and we need to model this interaction. And of course, we also have to deal with things like partial observability in a lot of situations, like occlusions and risk assessment and so on. So these are some of the challenges of this problem. And as part of this, what we focused on with CoverNet has really been on the multimodality aspect, and in particular on an output representation that is suitable in the context of driving. And at the time when we were developing CoverNet, the existing approaches at that point typically used CNNs to combine agent history with scene context and varied a fair amount in their output representation. The scene context typically included the past states of the agents along with high fidelity map information. On this slide, I focused more on the work that existed when we developed CoverNet, but I did also include some more recent references published after CoverNet. I'll start by mentioning stochastic approaches that encode choice over multiple possibilities by sampling random variables. One of the earliest works here frames the problem as learning a stochastic one-step policies, and it's reference 5 on the slide. We have R2P2, reference 7, that improves sample coverage by using a symmetric KL loss. Other work consider multi-agent settings like precog, reference 8 here. Other methods generate samples using conditional variational autoencoders or GANs. These types of approaches can be computationally expensive due to their repeated one-step rollouts. For one-step rollouts, they require both future rollout and sampling to obtain a set of possible trajectories. Although 11 on this slide does come up with an efficient way of dealing with them, but this was published after CoverNet. And also can potentially require a large number of samples for acceptable performance. And that can be often hard to determine in practice and can also depend on the scenario. To kind of move on, I'm not listing these references on this slide, but unimodal approaches also existed that would output a single trajectory per agent. And of course, this is unable to adequately capture possibilities in complex scenarios, at least most of the time. Even when you're thinking about predicting things like Gaussian uncertainty. And this is because these methods typically average over behaviors and they result in nonsensical trajectories, like for example, halfway between a right turn and going straight, which might be going outside of the drivable area. But multimodal approaches can output either a spatial temporal occupancy map, and these are 9 and 13 on the slide, or a distribution over multiple trajectories. Here we highlight 1, 2, 4, and 12. The first one, on the one side, occupancy maps can indeed flexibly capture multiple outcomes, but they can have pretty large memory requirements if we want to kind of sample the grid at a reasonable resolution. And it can also have issues with defining exactly how to sample the trajectories from the map. Multimodal regression methods, on the other hand, can easily suffer from mode collapse to a single mode. Reference 1 here, multipath, mitigates this by using a fixed set of anchor trajectories and then regressing to offsets. In contrast, CoverNet, for CoverNet, we frame the problem as classification rather than regression, and we contribute methods of creating trajectory sets to classify over. We do fixed, dynamic, and hybrid, and I'm going to go over them in a moment. And as part of this, the dynamic sets in particular, they exclude all of the trajectories that would be physically impossible to execute. So that's a great advantage to have. So our first insight for CoverNet is that there are relatively few distinct actions that can be taken over a reasonable time horizon. In our paper, we consider this to be 6 seconds. This is pretty standard in self-driving literature. And this is because we know that dynamic constraints considerably limit the set of reachable states over the standard prediction horizon. So there's only specific states that you can really reach based on your current state. And we also know that, there's inherent uncertainty, of course, in agent behavior, but this inherent uncertainty can outweigh small approximation errors. And our second insight here was that predicted trajectories should really be consistent with the current dynamic state. So what we do is we formulate our output as motions relative to that initial state. So for example, turn slightly right, accelerate, and we can then integrate this with a dynamics model and convert the output to an appropriate sequence of positions. And that's what we do for the dynamic sets. So our approach is to create a set of dynamically feasible trajectories and then classify over this trajectory set. And the main contributions include introducing this notion of trajectory sets, contributing the 3 different types, and comparing the state-of-the-art methods on new scenes, which is a public data set, and also on a bigger internal data set. And of course, empirically showing that the benefits of framing the prediction problem as classification. So to get into the actual architecture, here you can kind of see an overview of this. As I mentioned before, our focus is on the output representation with this paper. Similar to the MTP paper referenced on this slide, we use a scene raster input with map information. And this includes the past 1 second history for each actor in the scene. We use ResNet 50 as our backbone, and we concatenate the flattened result with the actor's current state. And this includes the velocity, acceleration, and heading change rate. We generate a trajectory set, which can be either fixed, dynamic, or hybrid. And then we classify over this trajectory set to get our predictions. And I do want to mention here, we can substitute the context encoder with anything really that we want. So we can use options that more explicitly model interactions like graph neural networks and things like that. Again, for this paper, our focus was the output representation. In terms of what the actual trajectory sets are themselves, we contribute 3 types. So we consider we're given or we have access to a reasonably large set of representative trajectory data from a training set, essentially. And what we want to do is to find the smallest fixed approximating trajectory set that still maintains a good coverage of this initial large set. And the 3 types of trajectory sets that we contribute are seen on the slide. The first one is fixed. We consider a trajectory set to be fixed if the trajectories that are part of that set don't change as a function of the agent's current dynamic state or the environment. And intuitively, this makes it easy to classify over since it allows for kind of a fixed enumeration over the set. But this may result in trajectories that are poor matches for the current situation. So they're not dynamically feasible. On the other hand, for the dynamic sets, a set is considered to be dynamic if the trajectories that it contains change as a function of the agent's current dynamic state. And this guarantees that all of the trajectories in the set are dynamically feasible. And finally, hybrid. This is essentially a combination between fixed and dynamic. And the reason why we introduce this is because unlike in the case of fixed trajectories, the synthetic nature of the dynamic profiles for the dynamic ones may not guarantee 100% coverage of that initial large set. And so we can find a covering subset for the elements that can't be covered by the dynamic choices. And then we combine the subset with the dynamic choices. And as you can see, the image on this slide kind of shows an example. To the left, there's a fixed trajectory set. And then to the right, there are 2 dynamic sets based on different agent speeds. So you can see how these differ when an agent moves at a lower versus higher speed. For the higher speed, the trajectories aren't as fanned out because the agent just cannot reach those states based on the dynamics. And this is really what the advantage that we're getting with this. How big do these trajectory sets need to be though? So we know that we can create these sets that approximately maximize coverage of the agent's reachable set, but the size of the trajectory set will grow with the length of the prediction horizon and the desired coverage level. But luckily, for self-driving and what we're looking at, we care more about 6 seconds into the future, right? And we kind of mostly care about getting close enough. Of course, there are situations where we do want higher precision, but in general, we kind of care about getting close enough. So what we found in our experiments is that we can achieve reasonable coverage. And when I say reasonable, I mean under 2 meters in maximum pointwise L2 distance for a 6-second trajectory with around 2,000 elements or even fewer in the covering set. And then the figure presented here, you can see that the number of trajectories needed to achieve 100% coverage of the trajectory set for different levels of epsilon, which is basically this tolerance that dictates the level of coverage desired. And you can see this for the fixed and the hybrid trajectory sets. And you can basically see that we need fewer trajectories for the hybrid sets in the set than for the fixed ones. And this is really showing the advantage of adding these dynamic trajectories. They're able to achieve the same level of coverage as the fixed ones, but need a smaller number of trajectories to do that. So how can we actually create these trajectory sets? We started by randomly selecting, again, this reasonably large set of representative trajectory data. Let's call it T. This comes from the training data. And we use a greedy approximation algorithm to find the smallest fixed approximating trajectory set. And we select a coverage metric, sigma, that in the paper we define as the maximum pointwise Euclidean distance between 2 trajectories, but this generalizes to any metric that you might want. We also select an acceptable error tolerance, epsilon, which basically represents the desired level of coverage. For the dynamic sets, we also create a set of control profiles, which I'm going to call L. And we do this by parametrizing the controls, so the output space, by a diverse set of constant lateral and longitudinal accelerations over the prediction horizon. And the desired lateral acceleration will correspond to different steering angles as a function of speed. And so that's why we use lateral acceleration instead of steering angle, just as a way of normalizing the output over a range of speeds. And then basically we have three components: the dynamics model, the control sequence, and the current state. And these three will determine the trajectory by forward integration. And that's how we get the actual trajectories. And in the paper, the dynamics model we choose as a standard vehicle dynamical model. But again, this is just a choice, so it extends to any choice you might have. And then to build the actual trajectory set, we greedily select trajectories from the initial large set T, or from the controlled profiles from L. This is for the dynamic sets. And this is based on how many trajectories from T can be covered with them. So what I mean by that is we cherry pick the best among candidate trajectories to place in the set that will be used as the covering set. And we repeatedly consider as candidates those trajectories that have not yet been covered, and choose the one that covers the most uncovered trajectories. And ties are broken arbitrarily when they exist. For the dynamic trajectory sets, it's very similar. The main difference is that the covering set here is constructed from the set of control input profiles as opposed to the elements of the T set themselves. And we terminate when every trajectory in T is covered. So this is kind of an example of the dynamic trajectories that you can see on the slide. So to move on to the results, the baselines that we use to compare CoverNet against are a constant velocity and yaw rate baseline, and then a physics oracle. And for the physics oracle, we use the track's current velocity, acceleration, and yaw rate to compute the following predictions: constant velocity and yaw, constant acceleration and yaw, constant acceleration and yaw rate. And the oracle is the minimum average point-wise Euclidean distance over these models. And then, of course, we also use the MTP and the multipath baselines that were references that I kind of discussed on the previous slides. We also extended the multipath model to use our dynamic trajectory sets as anchors. But we used the same number of modes that they used in the multipath paper. So this was 16 and 64 modes. We use both Gaussians and the internal data set that is approximately 10 times bigger in order to perform the analyses. And we look at a bunch of different metrics. On this slide, I'm going to present min AD at 5 and the hit rate. Min AD at 5 is the minimum average displacement over the top 5 predicted trajectories. And the hit rate, which we call hit rate 5 at 2 meters, is a metric that we use to interpret whether or not a trajectory was close enough. And this is computed over the top 5 trajectories. And for a single agent at a given time, it's 1 if the best trajectory in the top 5 trajectories has at most a point-wise Euclidean distance of 2 meters and 0 otherwise. And this is kind of like a proxy for joint performance with planning. So across the 6 metrics and the 2 data sets that we used, CoverNet outperforms previous methods and baselines in 8 out of 12 cases. This will be in the kind of the extended analysis, and I invite everyone to read this in the paper. But you can see in the figure here that CoverNet represents a significant improvement on the hit rate metric, with CoverNet significantly outperforming previous methods as the hit rate is kind of expanded over more modes. CoverNet also performs well according to the ADE. In the paper, we present this at 5, 10, and 15. And we see that this outperforms basically state of the art in every category. This restricted table shows it only for min AD at 5. But please read the paper in detail for kind of the full analysis. For a more qualitative view, this figure shows the visualization scene overlaid with predictions from our top models compared against the baselines. Again, we're using 6-second prediction horizon. You can see that the CoverNet predictions don't include straight trajectories here. This is because the vehicle slows down before the curve. We actually visualized this as videos, and we saw that it first predicted straight trajectories prior to the vehicle slowing down before that left turn. And then when it slows down, it predicts left trajectories. The image also suggests that the different alternatives for left turns for CoverNet are better captured in comparison with the baseline models here. I also wanted to present a bit of an extended analysis that we did in the follow-up paper to CoverNet, which is cited on this slide. And what we were interested in looking at primarily was how does CoverNet do compared to multipath, but with using many more modes? Because to remind you, we were looking at 16 and 64 modes per the implementation in the multipath paper. And for CoverNet models, we find that epsilon, for an epsilon value of 2 meters, so again, this is the tolerance for the coverage that we want. This is what offers us either the best or second best performance for all of the metrics in our on both data sets. And we find that a smaller epsilon value for the models tend to actually overfit, especially on smaller data sets like Newsians. For multipath, we find that the miss rate, and here the miss rate is really just the opposite of hit rate. So the lower is better. We just wanted to make it consistent with everything else. We can see that this decreases as the trajectory size increases. But however, using a modest number of modes, so 64, can still achieve the best value for min AD at top 5. And the table also shows the strong performance of the multipath approach with a large number of modes. So if you look at epsilon equals 3 and equals 2, even though the multipath paper noted decreasing performance with more than 64 anchors, we actually saw benefits by increasing this. And we wanted to analyze this a little bit further and try to understand why. And what we found is that the increase in performance associated with this higher number of modes might happen due to better coverage of space by anchors, by just having more anchors, leaving the network to learn smaller residuals. And in this table, the small table on the bottom of the slide, you can see that we display the average L1 and L infinity norms of the residuals learned by the model. And you can see that the residuals are basically smaller for the models that have a higher number of modes here. So to summarize for CoverNet, we introduced a novel method for multimodal probabilistic trajectory based on framing the problem of trajectory prediction as classification over a diverse set of trajectories. And this helped us do 3 things. It helped us ensure the desired level of coverage of the state space. It helped us eliminate dynamically infeasible trajectories, and it helped us avoid the issue of mode collapse. And we also showed that the size of our trajectory sets remains manageable over a realistic trajectory prediction horizon. And finally, we compared our results to multiple state-of-the-art methods on real-world self-driving data sets and showed that it outperformed similar methods. So to conclude this talk, we noted that obviously machine learning is a core part of self-driving technology. We looked at how we employ deep learning for motion prediction in order to reason about scene context, multimodality, and interactions between road users. And we also saw that we can use trajectory sets in this context to ensure a desired level of coverage and also, more importantly, dynamically feasible trajectories. What are our next frontiers? We're looking into tighter integration with planning and exploring machine learning planning-based methods. And we're also focusing on strong performance on corner cases because the long tail is really what we're trying to solve for. So with that, thank you to everyone for attending and listening in. We are hiring, so please check out our open positions on our website. And of course, I'm happy to take any questions. Thank you.
Thank you so much for that talk. I'm going to monitor the chat to see if there are any questions. Also, again, please feel free to unmute yourself if you have any questions. Luigi has his hand up. Luigi, do you want
hi, Corina. Thanks.
Hi.
Very nice presentation. Well, I have a question which is mainly related to the fact, so essentially how the network handles also the interactions between other agents. Because you talked a lot around, about all the feasible sets of the trajectories, but do you try to handle also those interactions? And can the network be applied not only for predicting, a single agent system, but maybe you can use it for predicting, predicting also the other agents? Yeah.
Yeah, great question. Yep. So I went back to the slide that kind of shows the overview of the architecture. So, technically speaking, I should say that interactions are captured implicitly because we, at the end of the day, add all of the information required for that as part of the input, as part of this rasterized image that we create. And the encoder, which in this case is, the backbone is a CNN, we use a ResNet for that, will implicitly capture some context and some interaction. That being said, this is not modeled explicitly. So after CoverNet was published, there were a couple of papers that were published, such as VectorNet, that kind of, they can use a different representation for the input. So for example, polylines instead of, this kind of rasterized input image. Our approach is not limited to this particular input representation by any means. So you can choose to change the input representation. You can choose to change the encoder. So you can use something like a graph neural network to very explicitly model interaction between agents. This was not the focus for this particular paper. We looked at output representations, but there's nothing really in this architecture that limits us to these choices. So basically, right now it doesn't explicitly model interaction, but you can substitute any of these components and use the output representation that we basically propose in the paper in order to give you all the benefits, but also allow you to model interaction in a more, explicit way. And then the second part of your question was about predicting for all the agents in the scene. So for this paper, all of these models, we were predicting for a single agent and we were centering on that agent. But this is, again, not limited to doing that. So you can apply, you can kind of think of different approaches to doing this. Actually, the multi-path paper kind of uses a two-stage approach where they applied the context encoder to the full scene, and then they crop around each agent and rotate such that the heading for that agent points upwards in the image. And then they will predict for all of the agents in the scene. So we actually, we also implemented that as a baseline for this paper. We just used, single agent predictions just because it was easier to kind of compute all of the metrics and compare across. But again, any kind of architecture that you might, think to kind of predict for everything simultaneously in the scene, this can be generalized to that. You just have to pay attention to kind of, make sure that the trajectory set is represented in the correct coordinate system because it's relative to that particular agent. So short answer is, in this paper, we don't do that, but it's straightforward to generalize to that.
Thank you.
There's a question in the chat. Have you considered conditioning the kinematically feasible, Have you considered conditioning the kinematically feasible trajectory sets on the map, essentially making the subset of map feasible or legal trajectories? This would probably require different representations of the input, something other than rasterized images.
Yeah, definitely. Yeah. So we have thought of, because you're right, at the end of the day, so these trajectories are all dynamically feasible, but at the end of the day, in terms of inference, at inference time, sometimes you might get trajectories that might potentially be outside of the drivable area because at test time, we don't ensure drivable area, kind of feasibility. So we have considered, we're kind of like, considering multiple extensions to this work. And I think that's a great, direction to go in. I will mention that, once the network kind of learns, after the point that it has converged, it should really learn to assign low probability to trajectories that are outside of the physical, drivable area. Implicitly. So implicitly, this is already happening, but there are ways to constrain this. And we actually have a follow-up paper that was the reference on the slide where I was talking about the extended analysis, where we did look into actually a particular loss formulation that can help with this. So if you want to, I invite you to check that out. But yeah, I think this is a great kind of direction, and it's definitely something that we thought about.
Wonderful. So for the sake of time, I think we should start